Yes. So my name is Thushadh Wijesekere, and I'm a PhD student from Lund University, and I'm employed at the Fire Safety Division in the university. So I will be presenting my project from this open forum course, and the title of the project was to develop a function object to calculate overpressure effects from delayed ignition of hydrogen jets. And in this presentation, I will give you some background and then describe the theory behind the calculation. And eventually, I will move on to the source code and the development of the function object. And I will end with showing some results on how this function objects how this function object outputs the calculation using a tutorial case. Yeah, so I will begin with the background. So hydrogen is a very hot topic these days for main related with the green transition. But hydrogen also comes with a few issues when it comes to safety, because it has some unique properties compared to commonly used fossil fuels. And one aspect is that hydrogen has very low energy density when it comes to volume. So this hydrogen has to be stored at extremely high pressures, and then these pressures can range up to 900 bar in certain cases. And if you have an accidental release from this reservoir, it leads to a hydrogen jet. And when you have an accidental release, you can end up with three different scenarios. One could be a case where nothing ignites, which is just a hydrogen jet, and the cloud is allowed to disperse in the enclosure or in the atmosphere, depending on where the leak is from. And if you have an immediate ignition of the jet, then you have a jet fire. But in this function object, we will focus on the scenario 3, which is related with the delayed ignition of the jet. So first you allow the cloud to develop, and then you have the ignition with the delay. And in that case, we have a gas cloud explosion, which creates an overpressure pressure wave, which could then be of concern when it comes to risk assessments and safety related calculations. Usually, when the leak coming from a pipeline or from a storage vessel can vary in sizes. It could be only a few centimeters, or it could be larger in certain cases as well. But regardless of the size of the leak, the jet will actually expand up to 100 meters. It may be even more if you consider the flammable cloud, because hydrogen has a very large flammable envelope. So the cloud is actually flammable in a longer span. And often the release velocities will be extremely high, and it could even be more than 1 kilometer per second, depending on the storage pressure, of course. And as we all know, the overpressure effects will spread 360 degrees across the domain. So it's not just a one directional phenomenon. And when it comes to assessing the consequences, CFD simulations are actually a very good tool to be used in this case. However, when it comes to the scenario that we are considering, we have very high velocities, and we have a very small release, and we have a flow that will actually react at certain point. And then we have to also consider a large domain, because we have to include the flammable cloud, which can span up to 100, even more than 100 meters in certain cases. And we can see how this could be challenging when it comes to CFD simulations. When you have very high velocities and a small release, you have to have a very refined mesh, and that comes with smaller time steps when associated with the higher velocities. And plus you have to then solve for the reactions as well. And in a normal risk assessment or like a consequence analysis, you have to consider multiple scenarios, maybe different release diameters and different release shapes or different delays when it comes to ignition. And maybe you will also need to calculate the effect of different weather conditions. For example, if you have a different wind, if you have different wind velocities. So these simulations can add up, and we also have to assume that we have to do at least one grid convergence study. So it could be very computationally demanding and time consuming, even today, even with the hardware that we have today. So the goal of this function object is to sort of simplify the calculation and then sort of recycle the gas dispersion simulations to calculate the overpressure effects directly. And in this function object, I implemented a certain method of calculation presented by these two people in, I guess, 2019. And the references are cited at the end of the slides if one wants to find the relevant citation. So, as I said, since we are recycling the gas dispersion simulation, we will not have any reacting flow. So we get rid of one issue, you could say. And also, since we don't have to extend the domain to the targets that we are interested in, we can also reduce the domain. For example, if we have a jet like this, and then we have to, let's say, measure the overpressure effects here. If one were to do a normal simulation, let's say that they also want to measure the overpressure effects here, they will have to have a domain this big. But in this case, you can have the domain just focus or just capturing the dispersion. So you can reduce the domain as significantly as well. So that also gives us some assistance when it comes to the efficiency of the usage of the computational resources that we have. And again, I used a function object for this purpose, and that means it is also compatible with multiple solvers in open form. And now I will move on to the theory part of the calculation. And here for this, the main concept that one needs to understand is this concept of detonation cell size. And we use this concept to isolate the region of the cloud which actually supports detonation. So this detonation cell size presented by lambda is a unique property for any flammable gas mixture. And it can only be measured through experimental work. You cannot measure it. You cannot actually numerically calculate it. And it depends, as I said, it depends on the mixture. So it depends on the concentration profile of the flammable gas, which can also be represented as the equivalence ratio, which is actually the fuel to oxidizer ratio in the actual mixture compared to the fuel to oxidizer ratio in the stoichiometric mixture. So if you have a stoichiometric mixture of fuel and the oxidizer, the equivalence ratio will actually be 1. And if you have less fuel, it will be less than 1. And if you have more fuel than actually needed, then it will be more than 1. And here I have focused on the reaction of hydrogen in air. So I take normal atmospheric air as the oxidizer, and that is also the experimental data that we have for this purpose. And I think everyone knows this, but I have included the reaction just to refresh. And if we then use these coefficients that we have here, we can then calculate the equivalence ratio, or we can derive the equivalence ratio for hydrogen in atmospheric air to follow this concept where YH2 is the mass fraction of hydrogen. Yeah, and the experimental data again is available at this Caltech detonation database, and I have cited the necessary work here in the presentation. And the concept of detonation cell size is shown here on this figure to your right. So you have the jet here, and depending on the concentration of the hydrogen, you will have a different size of detonation cell size, and usually it grows larger when the concentration decays. And it should also grow larger when the concentration gets higher as well, but yeah, it's not shown here. And in the zoomed in view, you can clearly see what I'm talking about. And this detonation cell size represents the transverse measurement of each cell. So for this purpose, I will use some experimental data. And the experimental data I have found are very old. So I guess no one will ever probably do any more experiments, given that it's, yeah, two people have done this in the 80s and no one really have done anything after that. And in this plot, you can see I can use the linear interpolation with the log of lambda to get intermediate values. But if you were to plot this in a normal axis, you would find the plot to have a very different shape. And then maybe linear interpolation is not valid, but when you do it with the log lambda, it actually supports linear interpolation. And this is important because in OpenFOAM, we can only go with linear interpolation. Yeah, and then, yeah, so I will be using this linear interpolation with the log scale for lambda. So the main purpose of the concept of detonation cell size is actually to capture the region of the jet which supports a stable detonation, or stable pressure wave. So three criteria has to be fulfilled. The first criteria is that actually the cloud should be the concentration should be in the flammable range, and for hydrogen it is this when you, and YH2 is mass fraction. And also the gradient of the detonation cell size should be below a critical value. Here I have chosen 0.1. And then also, depending on where you are in the jet, depending on the geometrical features of the jet, it has to at least contain 5 detonation cells in that region to support detonation. So we will then, in the function object in the development phase, we will try to isolate each criterion and then isolate the regions of the jet that fulfills these 3 criteria. So the region or the detonation can only happen if and only if these 3 criteria are fulfilled. So that we have to remember that we follow this logic, so to say. And to calculate the number of detonation cells fitting into a certain region of the jet, I used this formula. It's just very simple. So you just get the width of the jet and divide that with the local detonation cell size to get the cell size, to get the number of cells. And once we have isolated the detonable region of the jet, then we can get the mass of hydrogen in that region of the jet using cell values. Here I corresponds to the cell index, and V is the volume of a cell, and rho is the density of hydrogen. And once we have isolated the flammable mass or the detonable mass of the jet, then we can get the energy released by that mass using multiplying that with the heat of combustion for hydrogen. And once we have calculated the total energy release, then we can calculate the overpressure effects using this formula, where P star is actually normalized pressure by the atmospheric pressure. Yeah, and also one important aspect is that the distance. So this will give us the pressure profile as a function of distance measured by the geometrical centroid of the detonable region. So we will also have to calculate the centroid of this region at some point in the function object. So this function object was developed from scratch. I could not find anything similar already inside OpenFOAM, and I have given some basic commands to automatically let OpenFOAM provide you the templated files. So when you execute this function, this command, once you have sourced OpenFOAM, it will actually create this file structure. But remember, we have to include also the experimental data. So I will actually include experimental data to this structure, and you have to do that by yourself. Yeah. So in this function object, I will be using a few existing classes from OpenFOAM. One is the interpolation table, which is used for the interpolation of the data from the experiments. And I will also use this class tuple2 just to store the experimental data, which can then be read by this interpolation table class. And then I will use the functionalities given by this write file class to make sure that I can write the output into the disk. Yeah, so we have to include these required files, required header files in the function object in the source code. Yeah, and remember, we also need to calculate the equivalence ratio, which is not a direct output from OpenFOAM. You can easily calculate that using this expression field function object. Otherwise, I have also created a small separate function object called equivalence ratio H2, which you can use. But if you don't want to use that, you can just calculate the expression field you can self-calculate that using this function object, but this detonation cells function object should also support your calculation. So this is not a prerequisite. Yeah, and the experimental data that we obtain has to be in a certain way so that OpenFOAM can read it. So I have saved the data to a file called detonation cell size table, and they look like this. So on the second or the first index column, you have the log of detonation cell size, and the 0 index gives you the equivalence ratio. Yes, and then the experimental data has to be read. So this table I showed you before is stored as a public static member of the detonation cells class, and it should take this format, which can then be read by the interpolation table class. Yes. So this is defining the header file, and then we include the actual table in the .c file using these 4 lines. And this include statement just actually copies and paste the content of the file into this place in the source file. And once we have the experimental data ready to be read, then we can actually do the interpolation on the tabulated data. For that, we need to create a member of this interpolation table class, and it will be of scalar type. And then we also need a separate function to actually calculate the lambda the detonation cell size once we know the equivalence ratio. So this is a repetition of the previous slide, but here we have the calculation. So this function called lambda actually returns you the value, takes the argument phi, the equivalence ratio, and then it actually performs the interpolation based on this equivalence ratio, and then it returns it calculates the log lambda for the intermediate values, and then it returns the actual detonation cell size by taking the power of 10. And here is a place. Here is the place where I could see some improvement can be made for out of bounds handling in this class in open form. There is no option to make open form do extrapolation for out of bounds values. So here, OpenFOAM will throw an error, a warning if the values are out of bounds, and it will use the highest value that it can read as the value for out of bound in the out of bound regions. But I would say that one can improve this logic by implementing an extrapolation logic into this class and modifying the class. But I have not done that in this function object, but it could be done as in the future, for example. So when we use the function object in an actual case, in the control dict, you have to specify a few different fields. First, you should specify what your equivalence ratio field is. For example, if you use your own function object to calculate the equivalence ratio, then you should specify what the name of that field is when it's written to the disk. And here I use this safe lambda value entry to make sure that I don't run into any errors due to the out of bound limitations in this interpolation table class. And you also have to specify the orientation of the jet and the transverse direction of the jet. And then you can also specify the critical criterion, the second criterion. If you want to change it from 0.1 to a different value, you can also do that. And then you have to specify some planes, because when we calculate the detonation cell size, the number of detonation cells, I will slice the jet into a few different planes. So you can specify the planes, the number of planes. So this is more like a resolution for that calculation. So the higher the number is, the more resolved your calculation will be. And this R minimum and R max entries will take in the range of distance that you will be calculating the overpressure distribution for. And then these endpoints will control the resolution of the output of that distribution. And Pinf is the ambient pressure and heat of combustion. If you want to change that, you can also specify that in the control dict. Yeah, so criterion one is to see what the flammable region of the cloud is. So here I have taken the cells between this phi min and phi max. So this phi min and phi max actually represents the lower and upper flammability limits of hydrogen in air and the associated equivalence ratios in this for those two values. So first I isolate that value at that region, so we see where the criterion one is fulfilled. And now the second criterion is that we calculate the gradient of detonation cell size and then see if the criterion 2 is fulfilled. And for the calculation of the gradient, we need to use this header file in the source code, in the source file. And once we have the necessary header files, then we can easily calculate the gradient of the detonation cell size. And we have to get this detonation cell size in the direction of the jet. So we have to calculate the component, as you see here, and it is calculated as a dot product of the actual gradient and between the direction of the jet. Yes, and then we also focus on the absolute values of the gradient to see if it fulfills the criteria. And for the criterion the second criterion, we have to focus on the flammable region of the cloud, and then we have to see if it is actually stable when it comes to the second criterion. So if so here we apply the constraint on the second criterion and see if the absolute value of the gradient of lambda is below the critical value. And if it is if it is below the critical value, we mask it by applying a value of 1. Otherwise, it's 0. And once we have once we have identified what the critical region of the jet is, then we can move on to the calculation of the number of cells. The source code is quite long for this region, but the logic is basically you get the region of the jet which fulfills criterion 2, and then you calculate, then you specify the transverse direction of the jet, and then we, as I said, we slice the jet into different planes, and then for each plane we calculate the volume weighted inverse of lambda. And once we know that, and also the axial span of the jet and also the radial span of the jet, we can then calculate the number of detonation cell size using this formula. And the implemented logic actually works with multiple domains or multiple processors as well. So it will not be an issue if you have calculated the values on different processors. The source code should support multiple processors as well. Yeah, and here it's just the same logic as the one I showed you before. The only difference is now we focus on the n lambda field, which is the number of detonation cell size, and see if it is above 5. And if it is above 5, then we assume that's the detonable region. So the next step is to calculate the region, the centroid of the region, which is quite straightforward. So we isolate the value, the region where all three criterions were fulfilled, and then we calculate the geometrical centroid using a simple formula. And also, again, here, it doesn't matter if you are doing the calculation on different processors, it should also work that way. Yeah, so now we know we have all the necessary information to move forward. And the next step is to calculate the amount of hydrogen in that region, which, as I showed you before, is quite straightforward. We just multiplied the density of hydrogen or the mixture of hydrogen in the cell, and then with the volume of the cell and the concentration of hydrogen in the cell. Again, here the source code actually supports calculation on multiple processors. Once we know the total mass, and you will also specify this heat of combustion in the control dict, we can easily calculate the total energy release, and then using that formula with for pressure, you can easily calculate the pressure. And then remember, we calculated the pressure as a normalized quantity with respect to ambient pressure. So we have to multiply that with the ambient pressure to get the actual overpressure profile. So yeah, so now we have sort of completed the calculation, and now it's time to prepare the output. So in the output file, you will have the output file in the post-processing directory. Inside the directory representing the name of the function object. It depends on how you define the name of the function object in the control dict, but you will see a file for each write control. Depending on the logic of your write control, you should see a file for each time. And in that file, you should see the corresponding time, how much mass of hydrogen was actually supporting the detonation, and the centroid, and also the total energy release. And after this information, you will also be able to see the overpressure profile as well in the output file. So to compile the function object, you need to have this make files and make options files in the directory. So it will compile this source file, and then it will create this shared object in this form user lib folder directory. And in the options file, you have to specify all the different header files that we have used in this calculation, and all of them are included here. And here we can see how the control link should look like when you use the function object. This is just a repetition of everything that I showed you before, but this should be relatively straightforward. And if you refer to the tutorial case, you could actually see how this is implemented in the control link. So I will now finally show you some results and show you how the output looks like. So the tutorial case is a 2D hydrogen jet, which has a velocity of 2.5, and the diameter or the release size is 0.2 meters, 20 centimeters, and the simulation runs for 40 seconds, and the solver I have used is reacting foam for this case. And on the left, you can see the isolated flammable, the mass fraction of the flammable region of the jet. So here you don't have any values because there's too much hydrogen, so it doesn't support any combustion. And on this side, there's too less hydrogen, so it also doesn't support any combustion. And for this flammable region of the cloud, then you can see the field of lambda, so the detonation cell size. And then we go through the second criterion, and here we have isolated where the second criterion is met. So everything that is red is supporting stable detonation. And then here on the figure to the right, you can see how the detonation cells actually fit into the width of the jet, or the transverse direction of the jet. And here you can see the concept of slicing the jet in different planes. So here you can sort of distinguish different planes just by looking at this figure. Yeah, so here is an example of an output file. So all the information is here as a header, and then that header is followed by the actual overpressure distribution across the range of distance that you have specified in the control link. Yeah, so this finalizes the calculation. So of course, I did the calculations, but no one really knows whether this actually is correct or not. So we will do some experimental work this year. Actually, at least we plan to do some experiments, and then validate what I have done here. And as I said, I also intend to improve this out of bounds logic of the interpolation in open form, but that has to be implemented at a later point. Yeah, and as I said, you can find all the necessary citations as well in this presentation and in the final slide. So yes, I guess that was it from me. Thank you.